want to thank Jonathan and other organizers for putting together a great meeting, and thank you for staying for the last day. I know, several of you have other things to do today. So this is a work on applying a splitting method to pathological problems, which are those that may not have a solution, feasible but may not have a solution, being unbounded or infeasible ones. So we started this because when a few years back we were trying to use Douglas-Rachford and ADMM to solve conic programs where lots of the problem instances are pathological. And so if you want to write a solver for conic programs, let's say linear program, you need to handle these pathological cases, although they don't often show up. So what's surprising to us is Douglas-Rachford, not only we can say something about its behavior when you applied it to pathological programs, you actually have very nice behaviors. It tries to solve the problem as much as they can. So I'm going to explain why I say that Douglas-Rachford essentially works for most of the pathological programs. So Ernest Ree have to be back to give an exam today, so he's gone. He gave a talk yesterday on the impossibility results on operator splitting. This is also joint work with another student of mine, Yanni Liu. Okay, so. Okay, so here's a problem setup. We minimize the sum of two functions, f of x plus g of x, and also write down the dual. When you deal with pathological problems, we're going to often look at primal and dual problems together, because the property of the other problem also give you, for example, the certificates, or maybe tell you the existence of some kind of improving directions for the other problem. So we look at a pair of problems. So here is a standard Douglas-Rachford splitting. In my notation, zk is the main iterates. You start with zk and get zk plus 1. To get zk plus 1, you evaluate the procs with respect to f, which give you a point I call xk plus half. So the sequence that half, 3 halves, 5 halves, etc., is the sequence where I have evaluated the function f. And the other sequence, which is 1, 2, 3, etc. And those are the points where I have evaluated g. Okay, so x, these two sequences of x are also called shadow sequences, although the main iterates is z. Okay, so here's a classical Douglas-Rachford convergence results, which is a remarkably simple. It says this Douglas-Rachford splitting applied to, let's say, monotone problems. You're going to converge as long as there's a fixed point. In a paper about 5 years ago by some people here, they show that for the minimization problem, having a fixed point is equivalent to these three conditions. The primal has a solution, the dual has a solution, and the primal and dual have the same value. In other words, strong duality holds. Right? We also know from the 70s that if the Douglas-Rachford iteration does not have a fixed point, then it necessarily diverges, and it diverges unboundedly. So it appears that this is a complete result on Douglas-Rachford itself. Yes, it is, but we can still say a little bit more when you apply Douglas-Rachford to minimizing the sum of two functions. Okay, so here's the a summary of the new results. We basically say Douglas-Rachford will still work, and actually works pretty nicely when some of these conditions do not satisfy. For example, you do not need the primal to have a solution. You do not need the dual to have the solution. You can have unbounded problem. You can have infeasible problems. But one critical condition that, that makes nice results is the strong duality. In other words, the primal infimum is equal to the dual supremium. And these values can be minus infinity and plus infinity. And I will explain what I mean by still works, and I will relate these results to the rich results in the Douglas-Rachford operator community. So this, you can see this as extending the pathological results from the operator setting to a minimization setting. Okay. All right. Once we, if we have to do this for Douglas-Rachford, therefore, then we can translate these results to at least the classical version of ADMM. All right. So before I explain how it works, I have to define pathology a little bit carefully. So we say the primal dual pair is not pathological if those three conditions satisfied. In other words, once again, primal has solution, dual has solution, and strong duality holds. If any of these conditions are violated, then we say this problem is pathological. Well, it turns out it's possible to violate these conditions, certainly possible. So let's define the P star, the primal objective. So primal objective is infinity if the primal problem is infeasible. In other words, the domain of the function f and g do not have an intersection. Now, if primal is feasible, then there are two cases where it can have a bounded infimum or can have a lower unbounded infimum. If it has a bounded infimum, then P star is just that infimum value. Otherwise, when it's unbounded, we say P star is negative infinity. So P star going to have a range from negative infinity all the way up to plus infinity. So unlike linear programming, we're going to have some nasty cases which are associated to weak pathologies. For example, when the problem is infeasible, in linear programming, you're going to have a separating hyperplane which strictly separate the two feasible sets. But it is not necessarily true here, where the domain of the two functions may not have an intersection. At the same time, the distance between the two sets can be asymptotically 0. So you can think it as they don't meet at any finite point, but they meet at infinity. Now, when you have a finite infimum value, the solution may not be attained. And when you have a lower unbounded problem, it is possible you do not get a improving direction. In other words, you may not find a direction you can infinitely moving along which keep reducing the value of the function. All right. So you can see that this P star have whole range, and P star is always related to this value similarly defined for the dual. And we always have this weak duality, D star less than or equal to P star. But it's possible that this weak duality does not hold strongly. So it may be where you have a D star equals 0 and P star equals 1. There's a gap between primal and dual, which is going to cause lots of problems for Douglas-Rachford. So all the positive side of the results in this talk going to assume D star, going to actually deal with the case where D star equals P star. Yeah. Okay, so there are some pathological examples. We're not going to go to the details of these examples, but I'll just illustrate how these pathologies can be. So here's a conic program where you have a rotated segment on a cone. Right? Then you treat the cone as indicator function and call it g of x. And you treat the linear objective and the other constraint, x1 equals 1, as another function. So you can write it down as f plus g, and where these f and plus g are convex, proper, and closed. All right. And the problem, for this particular problem, it turns out it's lower unbounded. And it's very simple. There's a very simple proof I put in the footnote. So P star actually equals D star, which equals negative infinity. However, there's no improving direction. Here's another example where it involves the two functions. First function is 1 over square root of negative x. So you need x to be less than or equal to 0. And the other function is negative log x. Therefore, we need the domain, need the x to be strictly positive. Therefore, there's no feasible point. Right? However, the two feasible sets actually have no distance. Right? So the dual problem turns out to be feasible and unbounded. So in this case, you can say, by our definition, P star equals infinity, because in the primal problem is infeasible, D star also equals infinity. So we still say this is actually a strong duality, still satisfied, although the problem is pathological. Here's another example. In this example, both problems are feasible, and they have the same objective value, except the primal problem cannot give you a solution. It cannot attain a solution. It cannot have a solution that attains P star. Okay, so we have all these pathological problems, and frankly, they don't always arise in applications. But what I had personal experience is when I was working with Dong in about 2005, we were doing something called low-dimensional embedding, which is a topic in machine learning. So you have high-dimensional data, you try to find a low-dimensional manifold that fit most of these data. And it turns out that problem can be written down as a SDP problem. And because of the structure, I used a dual SDP algorithm by Steve Benson and Yingyu Yi. And for a period of time, I had a big trouble with the code because the code behaves strangely. Well, it turns out the reason is the primal is feasible, but the dual solution does not exist. It's the cone and the hyperplane intersect at one point. And because of the linear objective, it turns out the dual does not have a solution. So all of these pathologies, I mean, this is the example of that kind of pathology. But so what happens is you occasionally run into pathologies, but when you run into them, it takes a long time to figure out what the problem is. Often these codes behave strangely. Okay. What we wish Douglas-Rachford do, what's the best scenario that Douglas-Rachford can do in this set of pathological cases? Well, if the problem is approximately feasible, for example, it's infeasible, but it becomes feasible asymptotically, then we hope Douglas-Rachford will produce a sequence of points, x, the two sequences of x that they approach feasibility asymptotically. And if the problem has an objective value, let's say finite or negative infinity, we hope that the objective sequence approach that value, even though you may not attain that value. Okay, so here's an example. If the primal problem is weakly infeasible, and we want the two sequences to approach each other, right? Because they are, because you can think it as only feasible at infinity. So this two sequences are gonna diverge to infinity and become closer and closer. And if the problem is feasible, but the solution is not the objective value is not attained, or the problem is lower unbounded, what you want to do is you want this Douglas-Rachford to approach feasibility, and at the same time produce this approximate objective that to converge to that value. All right. So in some sense, there are always two parts of Douglas-Rachford. One part is to achieve feasibility. So the two sequences are going to try to get close to each other if they can. And the other part is to achieve optimality. So you want this objective to converge to the optimal in Fimo of the primal problem. Okay, so these are little informal. So let's be formal. So this is the theorem we can show. Now, if primal problem is weakly infeasible, that is the domain does not have a solution, but the distance of the domain is 0, then we can show that the two shadow sequence converges to 0 point. If the problem is feasible, may or may not have a solution, but the strong duality still holds, then we can show approach feasibility at the same time when the nim inf, we have trouble getting rid of the inf yet, but the lim inf of the objective converges to the optimal objective value. So we basically can say something for all the pathological cases as long as primal equals dual. When primal does not equal to dual, we have a conjecture, and we can say, we conjecture that this kind of limit, even if it exists, does not equal to p. It will be strictly lower than p, when p is strictly greater than the dual. Okay, so these are the overview of the results. There's some prior work which led to this result. The earnest work is when people started thinking about this kind of pathological problems in the operator setting in the 70s. The Paisley and Banian and many other papers in that period actually studies this kind of problem. And therefore, I think for a long period of time that people didn't pay attention to the first-order method behavior on pathological problems until around year 2014. That's the publication date by Bosch here and Morsi. And I hope Morsi is going to talk about some of these results in the next talk. All right. So And there are some recent results on specific case. That is on the generic fixed point setup. On specific cases where we have these results, so we have papers studying the pathological under two, when you want to find the intersection of two closed convex sets using Douglas-Rachford, what will happen if they do not have an intersection? And there are also a more recent paper on finding the intersection of two affine spaces where the intersection may be empty, and also more general convex feasibility problems. Last year we did some work on conic programming where the difference is there's linear objective. The conic program is linear objective with two kinds of constraints. One constraint is affine, the other kind of constraint is cone. So if you don't have linear objective, it reduces to these cases. At the same time, ADMM communities start to pick up some of these interesting problems too. We have 3 papers published recently. They mostly focus on conic programming problem, but some of them deal with quadratic objective instead of linear objective. Okay. Let's go to the very, very beginning of the study. So the start point of this thing is actually related to something called a Fimo displacement vector, which is the concept that existed since the 70s, but the name was coined in the paper below. So it basically says if T, this operator T, is firmly non-expansive, whether or not it's Douglas-Rachford, as long as this operator is firmly non-expansive, you can say this, the fixed point residual of this fixed point iteration going to converge to V, this Fimo displacement vector. Now, there are some possibilities with this vector. Now, what this is let's look at this. You have identity minus T, and look at the range of that. That is all the set of possible fixed point residual values. And then you take the enclosure of that and project and check whether 0 belongs to the set. It's possible that the origin belongs to the range without closure or only belongs to the closure part, or even the origin does not even belong to the closure, then you're going to project, you're going to get non-zero vector. So there's different cases. Now, if V equals 0, then you immediately know that the fixed point residual is going to convert to the origin, which for Douglas-Rachford immediately tells you that the difference of these two shadow sequences convert to 0. Therefore, you can say Douglas-Rachford is going to find approximate fixed point. All right, this is the immediate consequence. Now, if V is not equal to 0, then we need to understand what V means in the particular setting. Like our setting, when you minimize the sum of two functions. So one very useful result is from this recent paper, where it says that this quantity, this set you project the origin onto, can actually be written as the difference between the primal domains, take the closure, intersect the domains of the dual functions, again with the closure. Now, with a very simple argument, you can get the following results out of that theorem. If the primal is infeasible, in other words, there is no intersection between domain F and domain G, so this set without closure does not contain 0, then it turns out when you project onto this set, you only need to project onto that set. The projection does not depend on the second part. Now, which tells you that this Fimo displacement vector, where the fixed point residual converges to, actually is the shortest distance, represents shortest distance between one domain and the other domain, which immediately implies that the shadow sequence is going to narrow and until the distance between the two domains. In other words, applying Douglas-Rachford to the minimization of two functions, you're going to make the best effort to achieve feasibility. Okay, do as much as possible. However, there are other cases where you cannot directly or easily generalize from the operator result. Here are some other questions we ask ourselves and try to get results on. Now, if the primal is feasible but has no solution, either because not solution because no point can attain that solution, then we do know that this fixed point residual is going to converge to 0. But we need more work to actually say the objective converges to the best objective possible. There are also two cases which are symmetric, primal dual symmetric. So in this case, P is feasible, and the dual is strongly infeasible. This is the case where you have a improving direction, right? And then we need to use some tool to show that the Fimo displacement vector actually gives you a improving direction. Right? So this have to connect to the function values. Now to do this, we borrowed the tool, a traditional tool in conic programming analysis, which is called recession function. So the definition is, if you look at the directional derivative, where the direction is d, which you specify, and the point at which you look at the directional derivative is moving. It's the current point moving plus a distance times the direction. So you're looking at the directional derivative along the direction you move. So it turns out if x is in the domain of a function, then this limit does not depend on the point x. Right? So this limit, which is called recession, characterizes the asymptotic rate of change of f along this direction d. Right? So it's asymptotic rate because if you fix a finite alpha, this may not equal to the asymptotic rate. Now this generalizes the rate of change, which is a constant in the linear programming case. Okay. So why do we need this? Well, we need that because this recession function is going to help us connect the improving direction from its definition to Douglas-Rachford. By definition, an improving direction is a direction you add upon any feasible point going to give you at least a constant decrease. That we call an improving direction. Now, D is an improving direction for my problem if and only if you look at the sum of the recession functions of the objective is negative. All right. In other words, asymptotically. Right? Ah, C needs to be positive. Thank you. Right. Because otherwise it's meaningless. Right. So you have an improving direction, little d, if and only if you look at asymptotic change. Of course, you look at asymptotic change of these two functions, that sum is negative, which is intuitive. Now, it turns out this is very easy to deal with in the Douglas-Rachford setting. Now, and this happens, you have this d if and only if the dual is strongly infeasible. So, for example, we can get this. So when primal is feasible, dual is strongly infeasible. And then, then you have primal dual holds with strong duality, and where both values equal to negative infinity. Then it turns out this Fimo displacement vector can simply be a negative of the improving direction. So how Douglas-Rachford diverge can actually tell you this improving direction, which is meaningful because the Douglas-Rachford trying to reduce the value. But if there's a constant direction along which you can keep reducing the value, and then asymptotically you're going to line up with this direction. This is what it says. Okay. Now, so this is still a little abstract because it deals with the Fimo displacement vector in the fixed point setting. So how can we translate it into the function minimization setting? This is the result. Again, P is feasible, D is strongly infeasible. Then what you can say is one shadow sequence is going to asymptotically approach this is distance, asymptotically approach the domain of the other function, so vice versa. And if you look at the shadow point sequence, then the shadow point sequence is going to eventually move along this improving direction, plus little 1. Okay, 5 minutes. All right. So we can say similar results in the reflective case when the primal is strongly infeasible, dual is feasible. Now, most of these are pretty easy generalization from operator setting, but something you need to work slightly more when you deal with objectives, because there's this problem. So when you deal with operators, a fixed point setting, we usually have this. So in fact, we know if primal and dual are both feasible, you have this. The fixed point residual converge to 0 vector. Well, this is much like saying that some kind of gradient or sum of the subgradients converge to 0. However, gradient and sum of gradient does not mean function value convergence. All right, this is well known. So here is a very simple example. We have two-dimensional example, convex. So in this example, if you simply set y equal to x squared, then you're going to get, well, sorry. If you let y goes to infinity, of course, the Fimo is 0. But if you set y equal to x squared, then, of course, x squared cancel x squared, you still get constant value. However, the gradient actually going to approach 0. So a fixed point setting gives you gradient approaching 0, but does not tell you what function value, necessarily tell you what function value converges to. So you need a little bit more. I have no time to talk about this. This turns out to be an important part called the primal subvalue. This is how this strong duality relation enters this analysis. Right? So what our result is, so using convex inequalities and the definition of primal subvalue, we can show that if P is feasible, if primal and dual are both feasible, even if primal has no solution, you still have a asymptotic feasibility, and the objective going to converge to the primal objective. So in other words, Douglas-Rachford really did what they can to say about this problem. Now, the final thing, this is almost the final slide, is strong duality necessary? Okay. This is the problem that we naturally encounter when we do this kind of analysis. So primal dual, it turns out this is necessary because if P star strictly greater than B star, in other words, there's a duality gap, it turns out DRS going to produce a objective value that is less than P star. And we have lots of numerical examples on this, but we have not been able to show this, so we'll leave it as conjecture. If D star strictly less than P star, then Douglas-Rachford necessarily gives you a wrong asymptotic objective value. You're going to go below P star. The reason you can go below P star is because it produced two shadow sequences, and these two shadow sequences are not necessarily feasible. They're not equal, right? So you in the middle, you can get values that goes below the optimal objective value. Here are two examples. I'm not going to get into the examples, but on both examples, we numerically observe that limit of this sequence. So F evaluated at its own shadow sequence, G evaluated at its own shadow sequence. It always go below P star. It can be in the middle, can also equal to D star, depends on the step size, I wouldn't say step size, the parameter in Douglas-Rachford. Okay. So it seems primal dual, strong duality is a very, very important property for Douglas-Rachford to work meaningfully. So let me summarize. What I talked about is this archive paper is under revision. There's some citation problems and organization problems we're working on. But the result is Douglas-Rachford actually works expectedly when strong duality holds, including those pathological cases. When you have infeasibility, when you have unboundedness, and when the solution is not attained, when the objective value is not attained at a certain solution. We previously have another paper which also do this, but specifically for the conic program, where we can derive certain kind of rate of divergence, and then use the diverging sequence to numerically identify the weak pathologies. And for some of those pathologies, it does better than interior polling method based on primal dual homogeneous embedding. Okay, with this, I stop and thank you.